Hello, welcome back. In the next series of videos, I will talk about the monotonic stack. Let's start with this motivational example. This question is from Geeks to Geeks. The link to this question is in the description below. Given an array of integers length n, we are tasked to find the nearest smaller number for every element in the array. And if there's no such element, then we have to print -1. In one of the examples they provided, here is the array that we are given, and here is the array that we have to return. Let's walk through this together. For each element, we are looking for the smaller element immediately to the left of that element. So the first element is 1, and there's nothing on the left of that, so we put -1. The second element is 5. We traverse from 5 to the beginning of the array and we find the smaller element. So we found 1 and that's the value we put here. Okay, for this element, again, we traverse from right to left and we did not find a smaller element than 0, so we put -1. For 3, we find that 0 is immediately to the left of 3, so we put 0. This element, so again, we traverse from right to left and we find that 3 is the smaller element. We also have a 0 here, and we also have a 1 here. We ignore those values because we want to find the smaller element immediately as we traverse from that element to the beginning of the array. So the first smaller element we found is the one that we want to put in the array here. For the final element, again, traverse from right to left, and we find 4. The important thing here is the nearest. The nearest one is the one that we first encounter as we traverse from right to left, and it's the first smaller elements that we want to put in the result array. The way I did it just now is a brute force solution where we had to go through each element in the array, and then we had to iterate all the elements left of that element. This would have the runtime complexity of O of n squared. Now there is a better solution, and that is what we're talking about today. We are going to use a monotonic stack, and this would have a runtime of O of n. Let's walk through the solution together using a monotonic stack. So we're given this array. We know we have to initiate a result. That's the array that we're going to return. And also, I will make a stack. The stack here is, I put it sideways. On the left is the bottom of the stack. The top of the stack is on the right. We know that we have to use a for loop to iterate all the elements in the num array. Inside this for loop, we have to maintain a stack where all the elements are always increasing. First, I will explain how we maintain this stack, and then I will explain why we have to maintain a stack where the elements are always increasing. These are the 4 steps inside the for loop. The elements in the stack need to be always increasing. The top elements need to be smaller than nums of I as we are iterating through the nums array. And if the stack is empty, results of I equals to -1. Otherwise, results of I is equals to the top element. And then we put nums of I in the stack. Okay, let's go through the example together. First element, number 1, there's no elements in the stack. The stack's empty. So we assign the results of I as -1. And then we'll put 1 in the stack. Next is 5. The elements in the stack is always increasing. That's true. Top element is always smaller than nums of I. So 1 here is smaller than 5. That's true. There's some stuff in the stack. So we put results of I as the top element. So we assign 1 here. And then we'll put 5 on the stack. Next item is 0. We still see that the stacks are always increasing. The top element is not smaller than nums of I. 5 is greater than 0. So what do? We have to pop the stack until condition 2 is satisfied. So we have to pop 5 and then check. 1 is still greater than 0, so we have to pop that as well. Now the stack is empty. And then results of I is -1. And then we put 0 on the stack. Next element is number 3. Elements in the stack is always increasing. True. Top element is smaller than nums of I, true. And then the results of I is the top element, so we put 0 here, and then we put 3 on the stack. Next element is 4. Elements in the stack is always increasing, true. Top element is smaller than nums of I, true. So result of I is the top element, which is 3. And then we put 4 on the stack. Next element is 5. Elements in the stack are always increasing. True. Top element is smaller than num sub I. That's true. So the result sub I is the top element, so we put 4 here. And then we put 5 on the stack. And then that is the end of the array. Now it should be clear why we are maintaining a stack where all the elements are always increasing. Our job is to find the smaller elements on the left. That means we maintain all the elements that are smaller than the current one. When we need to find a smaller element, we can always pop the stack until we find such a smaller element. Furthermore, notice in step 4, we're going to put num sub I in the stack. That's why at step 2, the top elements has to be always smaller than num sub I. Once we put num sub I in the stack, the elements are always increasing. Now, let's convert step 1 to 4 into pseudocode. So here it is. Everything's happening in the for loop. The first 2 steps, in order to maintain this invariant, what we do is that while this item in the stack, we'll take a look if the top item is bigger or equals to num sub I. If that is bigger or equals to, then that means the invariant fails. So we have to keep popping the stack until the top element is strictly smaller than num sub I. For step 3, we're doing the result sub I assignment. This becomes a ternary operator in which we check whether the stack is empty. If the stack is empty, we assign -1. If not, then we just take the top element because that is strictly smaller than num sub I. And then step 4, we put num sub I in the stack. So the previous element is smaller than num sub I. When we put num sub I, elements in the stack, it is strictly increasing. Okay, let's talk about the runtime of this code. Notice that all the elements are added to the stack exactly once, and they will remove at most once. So this is an O of N operation. Okay, so we just convert the pseudocode to real code and submit the answer for the question. This Java code is provided in the GitHub links below. This is very similar to the pseudocode I showed earlier, and let's test if this works. And it looks good. Today we talk about using a monotonic stack to find the smaller element on the left of num sub I. Now suppose we want to find the bigger elements on the left of num sub I. What do we do? Well, we just change this part of the code here, and then we are good. This template is very versatile. Now suppose we want to find the bigger element on the right instead of the left. All we have to do is change the for loop so that we are starting with the last element. We are going backward from right to left. All the other code remains the same. For the next several videos, I will use this template to solve several LeetCode problems, and then finally we'll solve a hard LeetCode problem at the end of the series. Hope to see you there.